thank you for watching this video. So this video is going to be an extremely important one, because in this video what we're going to do is we're going to take this result that we came up with, that n must be greater than 2, and we're going to pick n equals 3, the minimum integer that satisfies the strong form of the Shumlak-Hartman criterion in MHD. And we're going to study, first of all, we're going to study what the profile looks like of this Z-pinch. And then we're going to show that this is in fact a magnetohydrodynamic equilibrium. Because I've received feedback recently from a highly respected theorist in the community, as well as some other highly respected individuals in the community, that have indicated that they are not convinced that what I have here is really a magnetohydrodynamic equilibrium. Now, some of that is on me, because in my manuscript I realize I use the words electron a lot. Electron current, electron flow, electron plasma flow, where typically in MHD we are treating the ions as being the ones that move. However, the reason that we do that is because ordinarily we arrive at ideal MHD. One of the things that we do is we neglect the electron inertia. And when you neglect the electron inertia, the momentum is borne by the ions. However, if the ions are immobile, or if the electron inertia is much greater than the ion inertia, for example, if the electrons were suitably relativistic, then perhaps the electrons would be the ones who are carrying the momentum in that case. So I realize that has set a lot of people off on edge, hearing electron plasma flow, etc., all over the place. But the reality here is that this is Bennett's equilibrium. So when Bennett is talking about the drift velocity, the two-fluid velocity, which is the ion velocity minus the electron velocity for a hydrogen plasma, this gives us the plasma flow, and this is the U that is in the Bennett profile, the Bennett plasma current. So by exchanging the density and this U, the U in Bennett's plasma current, we're just staying in line with what Bennett is saying, right? But you've got to say it with math. So that's what we're going to do here. We're going to solve the two fluid equations, and we're going to show that this profile, which, remember, we have uz of r equals uz naught over 1 plus chi squared r squared squared. Excuse me. And chi squared again is b over t. And we're going to just skip ahead to the end here. This is c dt over r cubed. Now, I just kind of skipped to the end, and physicists do that a lot because what happens is that physicists are doing the math that they've done over and over and over, and that their brains take shortcuts because it gets tiresome. As a physicist, one of the things that you realize very early on is just how important time is. I remember the first research I was doing was in Hun-Millikan theory. And the thing about Hun-Millikan theory is that you might think when you're doing Hun-Millikan theory that you're doing quantum mechanics, the Hun-Millikan theory of molecular orbitals, but what you're actually doing when you're doing Hun-Millikan theory is you're doing combinatorics, because you're thinking, what is the way that I can collect these terms to produce the least amount of algebra while still being correct? So that's what we're doing here. And remember that this CBT, that is related to the where the shear layer is located, okay, of this profile. And this R cubed comes from the fact that we are using a cubic temperature. So T equals TP over RP cubed R cubed, okay? That's our enhanced thermodynamic gradient. Our enhanced thermodynamic gradient here. This is the basis for it. And it is the minimum form that satisfies the strong form of the Shumlak-Hartman criterion. So we just plug this in to here, right? And what we get is we get that this is equal to UZ naught. I'm gonna do all these steps here. 1 plus CBT, and there's an R on the bottom now because there's an R squared here, quantity squared. Now again, we play the same trick, right? We do this all the time in physics and math. When you're trying to get a common denominator, when you're trying to do anything like that, what you're really doing is you're saying 1 equals, in this case, R over R. And that will give us a common denominator. As long as neither of these is 0, or as long as it's not 0 over 0, which it's not. So let's go ahead and do that. I'm just going to check real quick to make sure that the video is still on. Okay, good, it is. And so when we do that, what we get is we have UZ naught R squared R plus CBT quantity squared. Now, before I continue, you might be wondering, what happens if we just leave N as it is? And the one thing we need to be clear about is that, there's all these kinds of profiles that we can come up with to maintain the Bennett current, but they're not all going to be real. And that's one thing that we'll talk about later on that needs to be talked about, because if you can exchange the density profile to the flow velocity, then can't you do it partially? And the answer is yes. But there are some limits on these exponents. I won't talk about that yet. So this right here, this is the profile. I call it the cubic Pureflow Bennett vortex, or Bennett-Shumlak vortex, if Eulerian is not listening, or if you're okay with, if you feel okay with making him a little angry by saying Bennett-Shumlak in his hearing. Now, the most important thing about this for our purposes today, because you might think we're going to solve the two fluid equations, that's going to take forever. It's actually not, because we're going to use the fact that this is what is called an axisymmetric profile. It only depends on R. And it is also a purely axial flow. And those two properties are going to make the two fluid equations, together with the fact that we have a uniform density. Remember, now we have a uniform density because we swapped the Bennett profile. That is going to make this work out very nicely. So keep this in mind. Write it down if you need to, because I don't have much space to work with here. And the two fluid equations, there's a lot to them. So I'm going to write them down. I have Jeffrey Friedberg. This is straight from Jeffrey Friedberg, the first edition of his Plasma Physics and Fusion Energy. This is equation 11.2. All right? That's where I got these from. I have the book right here, along with the NRL Plasma Formulary. The NRL Plasma Formulary is one of the most useful, if not the most useful, pieces of literature in the entire canon of plasma physics, because it has everything that you need to do any kind of plasma physics that you want to do. So here's the thing about the two fluid equations, is they are 10, there's 10 equations here, and the first equation is continuity. We have the electron continuity equation. Now this equation is simply describing the fact that in a control volume, the flux of electron density moving out of that volume is going to be balanced by the rate at which it is changing locally in time inside that volume, right? Whatever point you're looking at. The same goes for the ions. And it's tempting to just kind of skip ahead, because what we're going to see is that because of the structure of what we're working with here, that we can cancel out a lot of this stuff. But I'm going to try and take this slow because it deserves some care right now. All right, so this next part, this is now the electron momentum equation. All right, so we have electromagnetic momentum right here, you'll notice that this is just essentially the Lorentz force, the bulk Lorentz force, all right? We have E, we have the magnetic force, and then we have a density to account for the fact that, well, it's the bulk instead of just a single particle force. And we've got a plasma pressure gradient, the electron pressure, as well as, I'm going to write this down just so that we're starting from exactly where Friedberg presents. We have a collisional term here that transfers momentum between the electrons and the ions. But the great thing about this is we are going to be able to neglect this term because we're going to treat the plasma as collisionless. The interesting thing about fusion plasmas is that we can sort of treat them as collisionless because they're so hot. They are so hot that we can do that. Is at least my understanding. I might be corrected, or that someone in the comments might, expand on that. Now the next thing we have here is we have the ion momentum equation. I don't even have a zero there. And the ion momentum equation can be written like this. So this term might be unfamiliar to you if you have not studied fluid dynamics, but what this term is just essentially the total derivative, the total time derivative, the Lagrangian derivative of the momentum, the ion momentum, with the assumption that you have a steady density, which we do. All right, and then of course we have again the bulk Lorentz force on the ions, connected to a pressure, an ion pressure gradient, as well as the same collisional momentum term. All right, I ran out of room there. Now this is where it gets a little bit hairy, but we're going to find out that actually with the energy equation, which we start with the electron energy equation, that most of it we can actually neglect in this equilibrium, which is amazing, because that's exactly what you want to do. You just want to be able to ignore things, right, and hope for the best. All right, now this part is the heat flux, and then on the right hand side we have some I'm going to say, I'm not even sure, maybe a power density. I think it might be a power density. I do not profess to be right about everything. I'm sure I say things that are wrong. I know I've written things down here that might make a plasma physicist go, what? But that's okay, because the thing about this equilibrium, as we're going to see, is that it is actually magnetohydrodynamic. That all these equations, all these variables, what we're going to find in the end is that it reduces to exactly what it is supposed to. Isn't that incredible? All right, so these are the mass, momentum, and energy, but that's just fluid dynamics. There's also magnetohydrodynamic character here, and that is going to be captured by Maxwell's equations, which here we are, remember, treating a plasma as a vacuum, which is actually a pretty good thing to do. This is Faraday's law. All right, next we have Ampere's law. And yep, here we go. And those are going to be rounded out by, my name for this is the name that Richard Barber, my electromagnetics professor for undergrad, coined. The SAD law is what he calls it. And this law down here, he calls it the SAD law because it means that there are no magnetic monopoles. That's what this law means, is that magnetic fields are divergenceless. They don't diverge. If you have a magnetic field leaving a volume, then somewhere else there's going to be a magnetic field line, same amount, entering that volume. There is no magnetic charge, so to speak, like there is in Gauss's law, where there's an electric charge. So it's the SAD law. Now the last equation here is something that plasma physicists use a lot, and it is quasi-neutrality, that the ion and electron densities are the same. Now I'm going to leave that up there for a minute because I want to get a drink of this delicious shake that I made for myself. So this looks like a lot. And it also fills up the whole board. So the first thing we're going to do is we're going to erase some of this stuff. And we're going to start by erasing this stuff, the collisional terms. We're going to treat the plasma as collisionless. So let's go ahead and get rid of that. Nu sub EI, the electron ion collision frequency, is 0. And then we also erase it down here, okay? Yes, excellent. All right. That made things better already. So remember that we have this situation. U equals Ui minus Ue, and that equals Uz of R, Z hat, where Uz of R is the cubic Pureflow vortex. Okay? Now, here's something very important in fluid dynamics. And when you study fluid dynamics in university, you realize that one of the main ways that we sort of classify flows is whether they're incompressible or whether they're compressible. So an incompressible flow is one where the flow velocity is sad. Actually, it's where it's incompressible. It doesn't diverge, which means that if I push on a volume of fluid, right, it's not going to exhibit a net divergence. It's incompressible. Compressible flow is when there is some kind of source, some kind of density term, for example, on the right-hand side. And that makes things much more complicated. The great thing about Z-pinches is that they are incompressible. Now, again, I don't have a lot of room here, so I can't write on everything that I want. But I am going to write that down. I'll see if I can find some space to do it. Here we go. I'll just erase this. And the reason that Z-pinches, the reason that Z-pinches are incompressible has to do with the fact that they are an axisymmetric equilibrium that is purely axial. Uz of R, okay? Because when you study the divergence in cylindrical coordinates, it's not the same as in Cartesian coordinates. There are these R's that you have to add into the right places, because otherwise you will not capture the curvature. This is a curved equilibrium, okay? There is an azimuthal angle. Everything is not a straight line. Now you can see immediately we don't have a use of R. We don't have a radial flow. This also, I'm going to go ahead and say, you could think of it as there's no breathing to the plasma, right? What's breathing? Radial motion of the cylinder of my body almost. So there's none of that. So this term goes away. I wish I had colored markers for this. Similarly, there is no swirl In fluid mechanics and dynamics, U theta is swirl. None of that in a Z pinch. And then we've got our axial flow, but it does not have a Z dependence. I'm going to take a moment here because one of the things that I did is I solved an air plasma streamer head using the cubic Pureflow equilibrium. I used the experimental data of this atmospheric discharge to obtain a cubic Pureflow vortex solution to it. But I noticed that in the Z direction, and not just in the R direction, there was the same kind of form. So that's kind of weird, and ideal MHD is kind of like that. But what matters is you can see we got 0, 0, and 0. So the divergence of U is 0. And now this is very important. I'm going to erase this, but please remember it. Divergence of U for a Z pinch is 0. An axisymmetric Z pinch. And again, axisymmetricity here refers to the fact that the only coordinate which matters is R. Theta and Z, the system is symmetric with respect to them. So why that's so wonderful, why it's so important here, is because remember this N and that N, first of all, they're the same, right? Let's write that down here. This implies that Ni equals Ne equals N. And furthermore, we have that N is just N, right? We'll call it N naught. That means it's uniform. That was kind of like a 6. Let me fix that. N equals, that looks even worse. I gotta tell you, I wish I had something larger than this board. So notice, that's uniform, which means this goes away, this Eulerian component, that goes away. And when I say Eulerian, so here's how you can tell. I remember another great scientist told us once, a group of students once, that they could not, one of the weaknesses they had was that they could not remember which one was Eulerian and which one was Lagrangian. So the way I remember which one is Eulerian and which one is Lagrangian, and also not to act like I don't have weaknesses. I have plenty of weaknesses. More than that scientist has. But the way I can remember that is because Euler is from a time when physicists were trying to predict the motions of the heavens. They thought that we're just going to throw up a coordinate system that's fixed and study everything in that coordinate system, and we'll be able to predict everything. So an Eulerian derivative, this partial derivative with respect to time, is about the change at a certain fixed point. Whereas Lagrange came along later on, and Lagrange was like, oh, this is actually much more dynamic, right? We don't just have a fixed coordinate system. We could fix that coordinate system to anything, and it could be moving. All right? So now also notice, because we have a uniform density, we can pull this out, we can pull that out, and we can also get rid of this. So you might see where we're going here, because if we pull this out, and we pull that out, then what we have is N naught, and we have the divergence of a velocity. But technically, it's not the same velocity as that. It's the electron and the ion velocity. So what we do here is, let's subtract this from that. And then what we'll have, right? So I'm going to name this 1, and I'm going to name this one 2. All right? So therefore, we have 2 minus 1 implies that we have N naught, the divergence of U, equals 0. Booyah! That's exactly what it is for an axisymmetric, purely axial flow like the Z pinch. So we are moving along now. We really are. which is good. Okay, so the next thing we're going to do is we're going to erase this because continuity is satisfied for this equilibrium. All right, when we talk about this equilibrium, what we can think of is that it's valid because it beam counts all of the plasma particles moving into and out of a volume. So the next thing is we've got to beam count our momentum. Those plasma particles moving into and out of a control volume carry some momentum with them in certain ways. So you notice there's a difference between here and here. I'm not going to go into why. I'm just working off of Freeburg. But what we need to do is we need to look at this. So first of all, we know that U of I has no time dependence. Okay? And so on that basis, we can go ahead and get rid of this. It doesn't matter what exactly U of I is. It's the ion velocity. Doesn't matter. It's just going to depend on R, and it's just going to be in the Z direction. Okay? Now you might say, okay, I come up with some pathological case where there's all these different kinds of time dependencies and blah, 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 right? That just in different directions that just shake out to being canceled. And to that I would say, why would you make it complicated like that? This is a Z-pinch. It's an axisymmetric Z-pinch. We're going to work with the ion and electron velocities like they're that too. Because if we do that and we find that we get a different answer than what we should be receiving, well, that's a problem. But we're not. Now the next part here is this. Now this is what's known as a convective nonlinearity. All right? Convective nonlinearities are nasty business in fluid mechanics. In fact, the vast majority of the research activities that go on in fluid mechanics to understand how fluids work and to progress the field concentrate on these convective nonlinearities. That most of the difficulty of Navier-Stokes, and I'm going to go ahead and I'm going to tell you something about this equilibrium, is that it is a kind of solution to Navier-Stokes. It is what is known as a simple flow category 1 solution. And what that means is that it's a one-dimensional solution, and doesn't solve it everywhere, but actually in the z equals 0 plane it does. And one of the biggest reason why this is able to solve Navier-Stokes it's a simple flow solution, right? It's not a three-dimensional solution. A lot of people, they get excited when they hear that you found a solution in Navier-Stokes, but what you must tell those people and make sure that they understand, let me check and make sure the camera's on again. Okay, good. This is a little bit of a long video, but that's okay. What you must impress upon these people is that the holy grail of Navier-Stokes is a three-dimensional solution to the full equations, right? Where we have a radial, a swirl, and an axial flow, for example, in the cylindrical case. And some people think that's not possible, some people do. Me personally, the stance I take is that if there was such a flow, what that implies is that in all viscous flows, if there was such a three-dimensional flow, and I think someone did find a three-dimensional solution recently, but I haven't looked into it, and there hasn't been a huge buzz about it. It got published in the Journal of Fluid Mechanics or something. Anyways, if there was such a flow, what that would imply, that was a solution, that would imply that there is this fundamental structure that we can find, a three-dimensional structure, in any situation where we have some kind of viscous fluid, right, that conforms to the rest of Navier-Stokes. Like I believe it's also a Newtonian fluid. Navier-Stokes is not the most complicated that you can get with fluids. Navier-Stokes actually is something that also already has some simplifications built into it. Anyways, so what we're going to go ahead and do is we're going to erase this as well, because a z-pinch has no convective nonlinearities. And now, what we're going to do is remember, n and n, okay? And what we should do now, and this equals 0, all right? What we should do now is we're going to add these two equations together, all right? We're going to add 3. We're going to call this one 3. We're going to call this one 4, all right? So 3 plus 4 implies that we have En, okay? And we're going to have E minus E, all right? One positive, one negative, okay? And now we're also going to have plus Ui minus Ue cross B. So that is the Bulk-Lorentz force. And then we have minus grad of the plasma pressure, where P equals PE plus PI, okay? So notice these electric fields cancel, which is phenomenal. We love that they cancel. We do not want to deal with those. But also notice that down here in Faraday's law, we don't have an unsteady magnetic field, because the magnetic field is going to come from Ampere's law. And Ampere's law is going to tell us, I'll get to that in a second, but Ampere's law is going to tell us that the magnetic field here is going to be purely azimuthal and depend only on the radial coordinate, which is very important because that will satisfy the divergence of B needing to be 0. All right, so this is what we've got. And so, and of course then this equals 0. So therefore, we have En U cross B equals the grad of P. What is this? What is this En U cross B? Well, it's just the current density, ENU, which implies that we have J cross B equals grad of P. This is the ideal MHD momentum balance. I just thought of something else, because like I was saying earlier, you could maybe try and say that, okay, sure that this is dependent only on R and purely axial, but what if these two terms had something different characters? Maybe they were unsteady themselves, but just in a way that canceled. But if that was true, then this would also need to depend on T in order for that to get in there. So I just feel like it's pretty solid to say that because this depends only on R and is purely axial, that these are too. And this is the ideal MHD momentum balance. So this is very important that we got here, because that's where we needed to get. All right? For a z-pinch, that gives us this equation. There's only a radial pressure gradient, and it is balanced by the Lorentz force. Okay? So, booyah, we got there. That is a very good sign. However, we still need to deal with energy. But before we deal with energy, we're going to deal with the rest of Maxwell's equations here, okay? So I'm going to erase this part right now, but just understand that where we got is that J cross B equals the gradient of the plasma pressure, which is exactly where we needed to get to. Okay? So here we go. I'm erasing all of this now. That's what I'm doing. It's getting erased. You can back up the video if you'd like to see it again or write it down. Really, the truth about physics is that you have to write things down. And there's actually been research done in neuroscience that shows that writing things down makes you learn them in a totally different way. And this is a big part of the reason why cognitive decline occurs with certain kinds of AI usage. Not all kinds. There are ways of protecting yourself. You must practice protective prompting if you're going to use AI. Me, I do use AI. I worked on AI. I like AI. It's very smart right now, but it is not a substitute for a trained human. And in my opinion, it never will be, because it will always be wrong about something. Whereas with humans, a human who is sufficiently trained and sufficiently canny can get away with sounding like they're not wrong. But an AI cannot. An AI is always going to be wrong about something. There's going to be something in there that's wrong. It's just a function of its construction. Deep neural networks are what are called universal function approximators. That's why they work. We've stacked together these hidden layers, and they're a cascade of linear algebra. And because of that, we can represent any function with that structure, but only approximately. All right, so just to recap, we have gone through and we have found that this satisfies continuity and it also satisfies momentum. Excellent. Really, the only questions left for us are whether they satisfy the energy and whether Maxwell's equations are satisfied. But there's also another question, because notice that there's heat fluxes in here, all right? So looking at this, we have a temperature, okay? So you might be tempted to try and do something similar, like adding these together or subtracting them. But the problem is that if you subtract them, then, well, I don't think there's actually a problem with subtracting them, because you'll have NE and NI cancel everything, right? Actually, I might have said that wrong. Anyways, we're not going to do that. What we're going to do instead is we're going to notice, because what you would have to do is you need to subtract this, or subtract this from that, because then you get the divergence of U. So why don't we go ahead, do I want to try that? No, I don't think I do want to try that. Instead, what I want to appeal to is I want to appeal to the fact that UI and that UE, they depend only on R, right? Because remember, just as I've been saying, that this U, it is axisymmetric, all right? We do not put in anything else. If this depended on T and that depended on T or Z or theta, it would have to show up in here, because it would need to in order to be fed into these. So these are also axisymmetric. And because of that, so first of all, let's talk about temperature real quick. The temperature is TE plus TI, and it is equal to T of R, and like we've talked about, TP over RP cubed, R cubed. That's the pinch radius, that's the edge plasma temperature. So these as well depend only on R, which means these unsteady Eulerian components, they go away. All right? We can also similarly eliminate these subscripts. Now what we're left with is something that looks like a convective nonlinearity, but isn't, because temperature is a scalar function, not a vector. Okay? So this scalar function, well, what does it equal? All right? Well, I have that written in my notes somewhere, I believe. Yep, here it is. So this scalar function is UE sub R, okay? Which there's none of that here, times the temperature gradient And I know that should, for completeness sake, be a that should be a partial derivative. So I'll just go ahead and do that. But remember that this is axisymmetric, an axisymmetric temperature. So only depends on R, right? So that we could put that as a full derivative and there wouldn't be any problems, but I'm just going to write this out. Okay? And what does this equal? Well, once again, it's the structure and the symmetries of this equilibrium that come to our rescue. This goes to 0. That also is 0. That is 0. Ain't got no swirl here. That's 0. And this is non-zero. And this would cause a problem because we don't know what the form of the electron plasma temperature is. We only know what the form of the one fluid temperature is. Okay, doesn't matter. We don't have this. We don't have a radial electron flow. It's gone. So this whole thing, it's 0. Woo. So let's go ahead and erase that. Sorry if I made anybody get frustrated, but I don't have much space here, so I got to erase things, just like this. And now I'm also going to go ahead and erase this. This term right here, I'm going to erase it for the exact same reason. That only depends on R. This only depends on R. This is only in the z direction. Therefore, by the exact same logic that we just did, it goes away. Now, what are we left with? Well, we still got these divergences. But that is not a problem. That is not a problem because we could do a number of things. We could try the same kind of tricks that we've been doing, saying these are axisymmetric. And I think a reason why you could get away with saying that they're the same as this kind of usually of R, besides what I've been saying to this point, is that the plasmas like to move collectively, right? So if and there's a saying in plasma turbulence that it's like a pea soup, where one pea acts as the soup for the rest of the peas. And so if you've got a bulk flow, well, these are going to be moving in the same way. And we know that a Z-pinch has it's incompressible. So we can actually go ahead and get rid of this as well, because those things are incompressible. And all we are left with is a statement of saying, what is the divergence of the heat flow? We don't know what QE and QI are, so we have to now add these together, all right? So we'll call this 5, and we'll call this 6. And we add 5 plus 6, and that implies that we have the divergence of Q, E plus QI, equals S, where S is SI plus SE, okay? And then, of course, this implies that the divergence of Q equals S. And that is exactly what we want to see. Because what we're going to do next is we're going to say Q is some uniform thermal conductivity, all right, times a temperature gradient, our temperature gradient. So Q equals Q equals that. Oh, let's check on the camera, make sure it's still going. It is very good, but I'm running out of space most likely. We're getting close to the end. So, what is this? What is the gradient of R cubed in cylindrical coordinates? The gradient of R cubed and cylindrical coordinates is just the radial derivative. So that is our cube. Excellent. But we've got to take the divergence of this and figure out what S is. And then the other thing we're going to do here is we're going to obtain an integral. We're going to integrate S over the pinch volume, because I've done that in the paper, starting from the ideal case and a 0D power balance, and you arrive at a general formula for the thermal power of one of these things, and you can do it as a function of n, the power of the exponent, and you'll find that n equals 3 is indeed the minimum energy case. And when we do this, we're going to find that we get the same answer that you get from the 0D power balance, which is what we need to get, which is what shows that this is a magnetohydrodynamic equilibrium, not non-physical, like it's been accused of being, right? Not MHD, like I've also heard people say. Guys, it's just the Bennett equilibrium, all right? But again, some of that's on me for saying electron everywhere, okay? So I admit that I've been saying electron everywhere, and there's a reason for that. That's not technically invalid, but it does go with what most plasma physicists think of when they think of MHD, and that's because the way I think of MHD, which I'm taking that to mean ideal MHD, is not all this stuff about the electron inertia going away and blah, 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 blah. It's simply that the magnetic Reynolds number is infinite, and that's ideal MHD, okay? So what is this? This is, and also notice there's one thing here that we're doing that is very useful, and that is the fact that this kappa perpendicular, and it's the perpendicular thermal conductivity because perpendicular to the magnetic field, right? So in the direction of the axial flow. It's uniform. If it wasn't uniform, the math would be more complicated. And then what we have here now is the divergence of r squared r hat. Again, this is a cylindrical coordinate system, so we have these curvature terms that we have to address. All right? I hope you all can see this. All right? So what this divergence gives us is only the part that is influenced by the only the part that is influenced by the radial component, because there's no other components. Great, that's easy. That is easy to calculate, right? And we just want to check my notes to make sure I'm doing this right. Yes, I am doing this right. Very good. This is going to give us S of R, because it gives us 9 minus 9. That negative sign comes from the definition, right? And that negative sign is there to capture the fact that heat flows from hot to cool areas. So we have 9, right? This is just the power law, 3r squared. R's can't, and R gets killed, and we just left with R on top. 9 comes out. That's what it is, okay? And this equals S of R. Boom. Very good. Very good. That's what we wanted. Now we're going to integrate that in a minute. But before we integrate that, I just want to deal with Maxwell's equations. We haven't been dealing with them yet, but we're going to. So first one we focus on is Ampere's law. Now, in a cylindrical coordinate system, I actually know this one off the top of my head. We have and with quasi-neutrality, okay, we have mu naught En U, okay, which equals mu naught J, right? And because of the axisymmetric nature, this is UZ, all right? Where this is JZ. So you can obtain B theta from this. I'm not going to. That's a whole different video. It's going to be even more algebra than this one. But you can. But the important thing that we understand from this is that B is purely azimuthal and only depends on R. All right? And that's very important. Because for one thing, it's unsteady. Okay? Therefore, this goes to 0. The right-hand side of Faraday's law goes to 0. What about the left-hand side? We have an electric field that is curlless. And because of the axisymmetricity here, the electric field, all right, the electric field as well equals E of R, and I'm just going to say an E hat direction. Doesn't matter what the E hat direction is, right? Because we can write the E hat direction as a sum of R hat and theta hat and Z hat components. So when we look at this curl of E, all right, so understand I'm going to erase Ampere's law now because Ampere's law gives us, and I'll put it down here, AL gives us a B, it's just azimuthal, all right? So I'm erasing all this because I need room to talk about the electric field. Oh, that's not good. I'm going to just kind of separate that from this implies, so we're not thinking the electric field implies something about the heat flux in this framework. All right, so this curl, it has 3 components. All right? We have 1 over R minus all right, that's a theta. And this must equal 0. Now the great thing about this is that E only depends on R. So we're going to go ahead and we're going to kill everything here that doesn't depend on R. All right? So this doesn't depend on R. This doesn't depend on R. Okay? Neither of these depends on R. But we also know that the electric field, the two-fluid electric field here, well, is it going to have a theta component? Is it going to have a Z component? If it did, that would influence the force balance. And it isn't. It isn't influencing the force balance. There's nothing wrong with us saying that it has no axial and no swirling electric field, okay? There's nothing wrong with that. If it did, our momentum balance would need to change, but it didn't. It canceled out of the momentum balance. So essentially what this is just a statement that the electric field is either uniform or 0 right now. And that is fine, because that does not interfere with the rest of the equilibrium. In the ideal framework, the electric field is going to be equal, all right, not to E of R times E hat, as I wrote down here. In the ideal framework, it's going to be equal to U cross B, okay? And that's going to be equal to minus UZ B theta R hat. So understand that by doing what we've done, we haven't contradicted ourselves at all. We have not contradicted ourselves because this is the two-fluid electric field from a certain perspective. In the ideal case, we have a different electric field based off of Ohm's law and our ideal fluid velocity, right? And this U is not the same as that U, so don't get it twisted. I'm going to erase this now. But the point here is that the electric field, it doesn't matter, and we found from Maxwell's equations that is fine. Maxwell's equation, like, yeah, it's uniform or zero, you know. That is good. That's what we want. And now, the last thing we need to check is whether the divergence of B is zero, okay? And this equals 1 over R But hey, guess what? The only component we have is the theta one, but it doesn't depend on theta, it depends on R. So again, all this goes away. That's all equal to 0. So what we've found is we're there. It works. It all works. It works because the Z pinch is incompressible and axisymmetric. It works because we don't have an electric field that we have to worry about. It can be uniform or zero. Well, zero, it can be 0, and it totally satisfies Maxwell's equation. All right, in a two-fluid sense. And then we find that the only thing that's left that matters now is what this S of R is. But we know what it is. So let's integrate it. Why not integrate that throughout the whole pinch volume? That will get us a value that characterizes, let's say, the thermal power of this equilibrium, okay? So I'm going to go ahead and I'm going to erase all this except S of R because it's been up there long enough. Let's integrate S of R through the pinch volume and see what we get. All right, integral over the pinch volume. And what this equals is it equals 0 to RP, 0 to 2 pi, 0 to L. And we have R, S of R, dz, d theta, dr. Okay, that's great. That's great because we know that immediately we have a factor of 2 pi that gets pulled out, and we have this preterm as well. So we have minus 18 pi kappa perp TP L over RP cubed, and then it's R squared. But hey, check this out. That's an easy integral to do. And guess what happens? When we do it, the RP's cancel. And we are left with this. And what you could call this is, I don't know, you could call it, I actually ended up calling it in the manuscript S instead of, you know, what's here, and what I call what's S of R here, I called in the manuscript capital Q. So if you read the manuscript, especially the supplement, read the supplement. That's where all the math is. That is Q of R in the supplement. Okay, but here I'm going to call it, I don't know, I'll just call it QT. Right, and I'll leave a little 3 here to indicate that this is the cubic Pureflow vortex. And that is exactly what we needed to find, because that's exactly what happens when you consider a 0D power balance in the ideal case. So that's it. We went through it, and we found that this equilibrium solves the 2 fluid equations. And obtains exactly the results that we needed. So that's going to be it for me here. This has been a very long video. Thank you for watching to the end. And please make sure to like and subscribe. I'll see y'all next time.